And how many people here are climatologists? Oh, good. So I'm going to talk about climate change in 2019. Physics trumps all. An update. I'll talk a little bit about kind of generically some background information on climate change. If you've seen this before, no fair guessing on some of the questions.
You can use this slide advance to remote.
It didn't advance it. I'll just use this. This is all right.
Okay.
So there are 4 elephants in the room. 2016 was the warmest year in the history of global record keeping. That's not in the history of the world or the Earth, but it's in the history of global record keeping, which is recent, relatively recent history. And that was the 3rd year in a row it was the warmest year. 2018 is likely the 4th warmest year in history of global record keeping. There's a pattern going on here. And the second elephant in the room is the IPCC report, October 8th in 2018, that covered the critical and important decisions and difficult decisions that will need to be made if the world is going to restrict climate change to 1.5 degrees centigrade. So that was in October. And then the third elephant was November 23rd. That's Black Friday. That's the Friday after Thanksgiving when the 4th National Climate Assessment Report was released, basically covering a lot of the same ground that the IPCC reports cover, put together by U.S. scientists from a variety of agencies. And then the 4th elephant is this guy. President Trump says he's too intelligent to believe in climate change. He wants great climate. Well, moving on from there, how did I get interested in climate stuff? Well, I grew up in Quebec partly, and this is where I spent my summers, Lake Choiseul in Quebec. And when you have a sky like that, you get tuned into the weather because you couldn't look at your phone, there wasn't any internet, we didn't even have radio, so you kind of got tuned into what the weather was doing. And that's me on the right. So I've always been kind of a weather nerd. And then I got into climbing, and so the same things apply when you're climbing as they do when you're out on a lake in terms of needing to understand the weather. But then the question is, well, how did I really get interested in actually presenting on climate change? Well, several years ago, I was the project lead on an environmental impact statement that the BLM and the Montana DEQ were doing. And so we had a contractor doing the EIS, and so my colleagues from DEQ and I would review what they'd put together, and then it would go forward as the EIS. Well, I was reviewing the climate change section, and I was pretty familiar with the science, but as I waded into the climate change section, I was going, what the? Well, the contractor who had written the climate change section was using blog science as if it were actual science. It's not actual science. And so I told him, that might have worked for other EISs that you did. It's not working for an EIS where I'm the project manager. And I rewrote the entire climate change section. And I decided after that, maybe I needed to be a little more proactive about talking about climate change to the mining industry, because the mining industry has historically been a little bit behind the curve in terms of climate change issues. So my first presentation on climate change was in 2011 at the Vancouver, British Columbia Acid Rock Drainage Metal Leaching Conference in November and December of 2011. And I followed that with a presentation at the International Conference on Acid Rock Drainage in 2012, presentation at the SME in 2013. I was author on the climate change chapter in Responsible Mining and SME publication. And then last October I did a webinar for SME on climate change and climatic uncertainty. So let's talk a little bit, let's get to some basics. Who, what, when, and where? Does anybody want to take a guess on when the greenhouse effect was discovered and who might have discovered it, and that's really the start of climate change.
Coal miners back in the planet.
Well, I'll give you a hint. He worked for Napoleon. Joseph Fourier. He was a French scientist and mathematician, 1824 and 1827. How about the role of carbon dioxide? John Tyndall, English physicist, contributions to molecular physics in the domain of radiant heat. He identified water vapor, carbon dioxide, and ozone as greenhouse gases. This is really one of the pivotal discoveries in climate change, climate science. But here's an interesting sidelight. Hurricane Michael came ashore in Florida, and Air Force Base, Tyndall Air Force Base was basically right in the middle of Hurricane Michael. Tyndall Air Force Base is named for a different Tyndall, but it's not hard to be reminded that John Tyndall was the one that discovered that carbon dioxide absorbs long-wave radiation that would otherwise escape into space. So another interesting sidelight is actually there was an American woman scientist, Eunice Foote, who had actually reached a similar conclusion only a few years earlier. And there's an interesting article in the Smithsonian magazine that discussed her work and her failure to get the attribution she rightly deserved for what really is a critical discovery in climate science. How about global warming? Svante Arrhenius, he was a Swedish scientist, Swedish chemist. And he was the one that first hypothesized that as we burn fossil fuels and put carbon dioxide into the atmosphere, it would warm the atmosphere. And being in Sweden, maybe he thought that was not such a bad idea. But he was the first one that proposed that. And he worked with Arvid Högboom, a Swedish geologist, because one of the things that he needed to figure out in terms of how carbon dioxide cycled was how does carbon dioxide cycle in the geologic epochs. So Arvid Högboom was an integral part of Arrhenius's work. Key players in the 20th century, Guy Callender, who was an English engineer, Roger Revelle and Hans Suess, who were American scientists, Suki Manabe, Richard Weatherald, who developed the first GCM, which is General Circulation Model or Global Climate Model. Gil Plas was a Canadian physicist. Suki Manabe, their first attempt at a global circulation model was in 1967. Suki Manabe is still the meteorologist at Princeton University. Here's the basics. There is little, and by little I mean there is little scientific dispute about the physics by which global warming occurs. Carbon dioxide and other greenhouse gases, water, and water is an important greenhouse gas, that's important to not forget. Methane, nitrous oxide, ozone in the atmosphere absorb long-wave radiation that would otherwise escape into space, thus warming the lower atmosphere and respective temperatures worldwide. And this is kind of the generic energy input, energy outflow diagram that you see in climate science everywhere. But the important number here is this one right down here. That's the imbalance. That's the amount of energy that we're absorbing in watts per meter squared compared to what we should be, which should be close to zero. And this is the chart you've seen of temperature models, projections from the IPCC reports, using a variety of different estimates in terms of whether we restrict fossil fuel burning or not, what those different scenarios are. Everybody's probably seen this in one form or another, but there are a whole bunch of different data sets that indicate warming. You've got surface air temperatures, you've got surface sea temperatures, you've got sea level, you've got ocean heat content, you've got specific humidity, and this is important, we'll talk about this a little bit later. You've got hemispheric snow cover, you've got Arctic sea ice, you've got glacial mass, all indicating pretty much the same thing. Well, then the next question is, how do we know that it's humans? That's a common question you'll hear when you're tuned into the denialosphere. How do we know it's humans? Well, we know it's humans 3 different ways. We know it's humans because of math. If you total up the fossil fuels that are put into the atmosphere and you track carbon dioxide in the atmosphere, they're pretty close. Chemistry. The other reason we know is that plants preferentially take up CO2. They preferentially take up the lighter isotope of CO2, which is carbon-12. So as you burn those fossil fuels, you change the ratio of carbon-12 to carbon-13 in the atmosphere, and that's what this chart reflects right here. And physics. If it isn't carbon dioxide and anthropogenic warming, what is it? Well, this is total solar radiation. And you can see there's not a lot going on in terms of changes in total solar radiation. Who's working on it now? Well, prior to 2016, a lot of agencies were. USGS, Reclamation, you name it, a lot of people were. In the United States, not so much anymore. Globally, the Intergovernmental Panel on Climate Change, you're probably familiar with some of the work that they've done, the most recent one being the report on global warming of 1.5 degrees centigrade, which came out in October. There's some other people that might surprise you. The World Bank, PricewaterhouseCoopers, and other key players in climate change issues are the global reinsurers. Munich Re is one of the principal global reinsurers. These are the people that insure insurance companies, and so they are really interested in climate change because if you look at what happened in California, there's a lot of insurance money that's coming out there. But even the mining industry is starting to catch on. This is from the Australian Mining Bulletin, Managing Risk Posed by Climate Change. One of the other things that we're starting to see a lot more of in climate science is attribution, and that is identifying specific events and how they relate to a changing climate. So this is in 2014 from the American Meteorological Society. And then this is just, if you Google climate change risk in the mining industry, you get a fair number of hits. So does it matter for the mining industry? Well, it probably does. And this is what we're looking at here is in Montana. This is the Zortman-Landusky mine site, and we'll talk about that in a little bit. But the principal thing to keep in mind is that changing climate leads to changes in extreme weather and climate events. And we'll talk a little bit about the polar vortex also. A couple other things, again, keying off on this attribution work. Again, attribution of extreme weather events in the context of climate change. And then Union of Concerned Scientists also has done some work on this recently. Climate models do project there will be more heavy rain events throughout the 21st century. And the changes in precipitation have been manifested already. We already see that. This chart is from the National Climate Assessment that was just released in November. So these numbers are basically current in terms of changes in the intensity of precipitation in the United States. There are a bunch of other metrics. We'll spend a lot of time talking about these. Insured losses from catastrophes. This is broken down into different categories, and the principal ones are not geophysical events like earthquakes, volcanoes, things like that. They are meteorological events, hydrologic events, and climatological events. Those are the things that are changing. Significant weather-related U.S. electric grid disturbances. This chart is a little bit dated, but things haven't changed much as it's updated. global billion-dollar weather disasters, and these are adjusted for inflation. So you can look at that and see there's a general trend upwards. Last year there were 39. But why do we see more extreme weather events in a warming climate? Well, we see more extreme weather events because of the Clausius-Clapeyron equation, which basically says a warmer atmosphere holds more water. More water, more energy, more extreme events. But a couple other things that are interesting that may play a role in extreme weather events is Arctic sea ice loss. This was actually from a year ago, and it talked about the polar vortex from a year ago. And has anybody been watching the news? What do you know? It's back. So there's a lot of research going on right now about what role does the loss of Arctic sea ice and the warming of the Arctic play in terms of global atmospheric circulation. But there's another thing that also is an interesting research topic, and that is the increase in atmospheric blocking events. And these are circumstances where normal atmospheric flow, for whatever reason, gets blocked up, and it's like a traffic jam. And some of the recent extreme weather events have all been linked to blocking events. Montana in 2011, we'll talk a little bit about that, but some of the other ones you might be familiar with is Hurricane Sandy, Alberta, Canada in 2013, and central Colorado in 2013, extreme flooding events. Houston, Texas, Hurricane Harvey, 2017, and both Florence and the Texas flooding in 2018 were probably related to blocking events. So this is 2013. The flooding event in the Southern Rockies by Calgary, $6 billion, 2013, and then in Colorado, $4 billion. And if you draw a straight line between Calgary and Colorado, we're close to the middle there somewhere. So, and then of course in Montana we had some extreme flooding events in 2011, but they weren't concentrated around urban centers, so the dollar costs were quite a bit lower. I'll continue to do what I can, come hell or high water, expect both. So here is just some fairly recent news events of hell and high water. So these are just some of the papers that talk about Arctic sea ice loss and blocking events and what role they may play. And then also in relationship to the polar vortex, evidence is mounting that Arctic sea ice loss can affect weather and climate throughout the northern hemisphere. This is a 2018 paper, and this post here is from 2018. But wait, there's more. These polar freezes are happening more often, and they may be tied to climate change. This was only a few days ago. So it's a good idea to kind of pay attention to these and pay attention to the science, because it's ongoing as we speak. Now this is information from I talked with the fire meteorologists over in Missoula, and they're starting to see in the summer stronger ridging, which influences fire behavior and overall smoke in the western United States. So this is again something else that's potentially related to changes in the atmospheric circulation. But like I say, this is something that's ongoing now. People are working on it, trying to figure it out. Both the models and the observations suggest this signal has only recently emerged from the background noise of natural variability. So we're doing the experiment now, and there's no planet B. But pay attention to the science. If you're interested in this sort of stuff, pay attention to the science. If you see an article in the Washington Post or the New York Times or Huffington Post, a lot of times they'll link to the actual scientific article, and that's You know, some of this stuff, it's coming up all the time. So, what does this mean for mines? Well, a bunch of stuff means warmer temperatures. You know, if it's a degree or two warmer on a day at a mine, how much difference does that make? Maybe not much. More precipitation? Maybe. More frequent drought conditions? Yeah, maybe. More extreme weather events? Almost certainly. And for northern climates, loss of permafrost. That's important if a mine is in northern Canada and it's depending on frozen permafrost for travel. Because if the permafrost is thawed out, you can't travel. Or ice roads. For coastal operations, higher sea levels and associated storm surge. So really what probably matters most for the mining industry is more frequent drought conditions, because that will make reclamation ever more challenging, and more extreme weather events. And that'll impact mines in two ways. That'll impact mines just in terms of the overall need to think more about having more extreme weather events, but also in the back of a company's mind, they should be ready for something really extreme, like something that happened in Colorado or Calgary, a really extreme weather event where they're getting a lot of rain. And then in the West, fires. This could potentially restrict when a mine could operate, or it could restrict how they operate. I'll talk real quickly about this because it's kind of fundamental stuff. The following mine life cycle events should be evaluated for relative risk, and this is pretty straightforward. I mean, you can use your imagination and think that if a company is doing exploration, they're there for a short time, the surface disturbance is limited, it's not a big deal probably. Equipment is mobile, you've got people there, you can deal with something if it comes up. When a mine is under development, it's a little bit different because they probably don't have all their water management facilities and structures in place. If they have an extreme event, they could be in big trouble. While a mine is operating, the risks, you know, there are risks, but by the same token, they have staff there, they have equipment there, they can deal with stuff as it happens, and sometimes it does happen. Closure and post-closure, virtually all constructed features, reclamation, water management, water treatment, virtually all those structures are potentially at risk. The risk is highest before reclamation is complete, and the facilities may be in salvage. When you've got fewer people there, fewer equipment there, lots of stuff can go wrong. The longer term risk, counterbalanced by the longer time frames, you may have reclamation in place, but it's got to be there essentially forever. It's basically in perpetuity, so extreme weather events may or may not happen at the specific site. Foreseen or unforeseen changes in temperature precipitation patterns may dramatically impact vegetation and cover performance. I'll talk a little bit about that as well. So let's take an example from Montana, and we'll talk just briefly about this. This is Zortman-Landusky in May 2011. This is Wayne Jepson from the Montana Department of Environmental Quality, who was one of the folks from the Hard Rock Bureau who's worked at this site for a long time. So Zortman-Landusky got what essentially amounted to tropical storm rain totals over the course of about a day and a half in May of 2011, May 20th and 21st. They got like 11 inches of rain. That's a lot of rain for Montana. So one of the things that happened was this dump, the Carter Alder Gulch waste rock dump, was washed out. About 43,000 cubic meters of material were washed down this gulch and ultimately washed somewhere else where they didn't want to be. And the other near catastrophe was the Swift Gulch water treatment plant. Swift Gulch drains onto the Fort Belknap Indian Reservation, so it's a pretty sensitive drainage. Another thing to back up here, this site was a bankruptcy site. Pegasus Mine operated this until 1998 when they went bankrupt. So basically everything that's that's happened here has either been paid for by the reclamation bond money, or it's been paid for by public monies spent by the Montana DEQ and the U.S. Department of Interior Bureau of Land Management. It's public money that's been spent. So public money was spent to build this water treatment plant, and then in May of 2011 it was nearly washed out. So this drainage was washed out to the point of it was scoured out about 3.5 meters. The total repair cost of this, just to get this back in operating condition, was about $250,000. The total repair cost for site-wide repairs was about $500,000. And that, like I say, that's public money. And if you think about the Little Rockies, they're a small range, but basically there were anything that was constructed, all the roads, all the water management features, basically all had to be repaired or reconstructed. So site-wide miscellaneous repair costs were in the neighborhood of $100,000. Again, total repair costs are about $500,000. But it could be worse. This is in Australia in 2011. These are coal mines in northeast Australia. This is an excavator. And this is another excavator, digging out the excavator. These are haul trucks. So I say, it could be worse. I think the total damages to the Australian coal mining industry from this were over $1 billion. So let's talk about what matters most for mines: more frequent drought conditions and more extreme weather events. So for Montana, if you're looking at the NOAA Storm Atlas for Montana to try and figure out how much rain do we have to worry about, here's what you're going to look at if you're not paying close attention. You're going to look at the precipitation frequency atlas for the western United States, Montana, 1973. Well, look at that, and then this is actually the observed change from not the fourth National Climate Assessment, but from the third one. So these numbers are actually a little conservative compared to the more recent climate assessment. So things are changing. 1973 is not very helpful. So the most recent update to the NOAA Storm Atlas was in Texas, September 2018. And the change in Texas, the important number in Texas is 100-year. What used to be a 100-year event is now a 25-year event. Now keep in mind that the amount of moisture that's available in Texas is a lot different than the amount of moisture that's available in the northern Rockies, because Texas has the Gulf of Mexico right there. But the physics are the same. So there's no reason why in the northern Rockies you wouldn't see the same thing, a 100-year event, what used to be a 100-year event become a 25-year event, which means a lot more rain. These are some conclusions that I put together for one of my earlier talks. Industry is making closure, reclamation, and drainage treatment predictions based on a historic climate that no longer exists. It will be important for mining companies to plan for extreme weather events as a contingency throughout the mine life and design their closure plans to survive them. So let's talk about what this means for Montana. Well, it's pretty straightforward. It means shorter, warmer winters. It means longer, drier, and hotter summers. It means more winter precipitation as rain. It means less frequent rain in the summer, and it probably means more intense rain events when they happen. So let's take a look at what this would mean for Montana, what this will mean for Montana. Projections for stream flow timing. This chart is the observed shift in stream flow timing. And what this is telling you is that high flows are coming earlier and low flows are coming earlier and lasting longer. That's not good for fish. It's also not good for floating if you're a floater. And then these are the projected future shifts in the timing of stream flow. And again, it's the same thing. You're going to see You're going to see more water leaving early. You're going to see lower water flow later in the year. And that's a big deal. For example, in the Northeast, on another aspect, northeastern U.S. ski resorts estimate only 4 out of 14 major ski resorts will remain profitable by 2100 under the high emissions scenario. So here's an interesting sidelight. Campaign donations link ski industry leaders to climate change deniers. What? But anyway, look at the projections for snow cover, historical, mid-century, and end of century. And again, what this translates to is low stream flows later in the summer, among other things. So this is something that fisher people and floaters are concerned about, and of course skiers are concerned about. What does this mean for Butte? Well, again, it means sort of the same thing. Shorter, warmer winters, water, water, water. Where's the water going? Another thing, kind of another interesting sidelight to this, and this is something that my friend Rick Appelman and I had talked about, is it used to be in Butte, a lot of the winter was below freezing. And so the difference between a winter where a lot of the winter is below freezing and a winter where it's above freezing almost every day is really hard on the roads. And so that's a consideration that probably a lot of people haven't thought of in terms of road maintenance and road degradation, because every time it thaws and freezes, it's a little bit harder on the road. So the next thing it's going to mean is longer, drier, and hotter summers. Where's the water? Again, linking back to those reduced late season stream flows. More winter precipitation as rain. That's going to translate to kind of shitty skiing. If you're a skier, you're not going to think much of that. Less frequent rains in the summer. That's probably going to mean more smoke, as we've seen recently. More intense rain events when they do happen. Potentially more erosion and washout issues. Again, look at the historical snow cover and projected snow covers, and that's what we're seeing. So, what does this mean for Butte in terms of Superfund and restoration activities? It probably means your vegetation is going to spend a lot more time when it's dormant. It's going to mean that your vegetation is going to spend a lot more time when it's under stress because it's not getting as much water as it would like. It's going to mean you may have, as the climate changes, you may have the wrong mix of vegetation species. It could mean weeds. And all of this leads to poor cover performance. And the critical aspect of poor cover performance is really two things. Most covers for waste materials at mine sites are designed to store water. They're evapotranspiration covers. So they're designed to store and evapotranspire the water. If the vegetation is not effective in doing that, that's going to mean that more water is going to go into your cover system and it's going to go through your cover system. Because the idea behind an evapotranspiration cover is that water is contained in the cover system and basically cycled in and out. It's designed to essentially not allow much water to go through the cover and into the waste material, because all the water that goes into the waste material potentially will interact with the waste material and ultimately need to be treated, which could mean that you're going to need more water will need to be treated than you'd projected as you constructed your covers. And that's a big deal because water treatment is expensive. The other thing it means potentially is if your vegetation isn't performing well, you may not have the vegetation cover you really want or need, and you're going to have erosion. And then potentially you'll have erosion and wicking of contaminants during dry periods, or you'll have mobilization of contaminants as stuff is eroded in heavy rains. So what can we do to design some resiliency into what we're working on? Well, the first thing we can do is design your landforms, all your reclamation, restoration landforms, to have some component of actual geomorphology. In other words, they need to replicate how actual landforms function. If you drive over the hill and you look off to the east as you come down from Homestake Pass, you'll see the west slopes of the Golden Sunlight Mine that were reclaimed about 25 years ago. And they're really linear, and they've got linear diversion ditches. You don't see that in nature, and there's a reason you don't see that, because that's just not how geomorphology works. So you need to incorporate actual geomorphology in how you design your landforms. And when you do that, you will end up with a complex landform system, not a series of linear slopes. And then what you will do is you'll do a detailed evaluation of the soils, aspect, slope, and the microsite characteristics, and you'll make your reclamation species planting based on those detailed evaluations, so that you get the best species at each individual microsite. And you're going to want to plant species that are specifically adapted for the climate you anticipate. So you're going to want probably droughty species. You may have to look ahead a little bit and make some adjustments as you develop your reclamation species, and that's where I defer to Robert. The other thing companies will have to do, and this is something you really can't avoid, because there will be areas where they have to construct water management features. And so they'll have to design basically everything that deals with water management to be engineered for more intense rainfall events. And at some point, there's a break-even point. You know, if you're designing a road and you're designing it for a 25-year storm event, at some point, it's cheaper to figure, if we get a rainfall event much bigger than that, hell, we'll just put in a new culvert. It'll wash out and we'll put in a new culvert. So there's going to be a break point where the cost of basically replacing the whole structure is the simplest thing to do. But nonetheless, you have to figure, we're going to have to deal with more rain. How are we going to manage that? So that's one thing that's important. The other thing that's important is for a mining company to think about, okay, we're going to routinely deal with more intense rainfall events, but what do we do if we have a really serious rainfall event, so that we don't have a tailings dam failure like happened in Brazil last week? Things that kill people. Those are things that companies are going to have to think about in the back of their mind about how do we incorporate those sorts of contingencies for really extreme events where people might die. It's not a question of reclamation. It's not a question of, how can we do this a little cheaper or whatever. It's a question where if you don't do it right, people might die. So those are things that companies should have in the back of their minds about, okay, if we have a really intense rainfall event where we're getting tropical storm amounts of moisture over the course of a couple days, what can we do to keep people safe? What can we do to avoid as much as possible damage to the environment, long-term damage to the environment? So those are things that are going to be important. And the other thing that's going to be important is, as the climate changes, ongoing and continuous monitoring to see how things are doing. It's Calvin. And then this is just a blogger. Honestly, climate change scares the heck out of me and makes me so sad to see what we're losing because of it. Maybe you should learn some actual science then and stop listening to the criminals pushing the global warming scam. I don't know, man. I already went and got a PhD in astrophysics. Seems like more than that would be overkill at this point. Yeah, probably. So here are some general resources. If you're really interested, let me know, and I'll make sure I'll email you a copy of this. This thing at the bottom is a really excellent graphic that details how we know it's humans. And what they do is they They look at a timeline and they say, okay, well, is it the sun? And they'll show the sun down at the bottom doing not much. Is it volcanoes? And they'll show the volcanoes at the bottom, and it doesn't do much. And they'll show that, they'll compare that with the temperature. So it's a really excellent graphic that kind of puts things in perspective in terms of, well, how do we know it's anthropogenic, and how do we know it's people? So that's a good one. These other ones are all good sites, and they're science-based. They're run by actual scientists. I would recommend them highly. That's all I got. If you've got questions, I'm happy to try and answer them.